Let's dive right into this explainer and uncover the hidden infrastructure powering the modern AI revolution. We always hear about the mind-blowing things AI can do, right? But we almost never peek behind the curtain to see the actual physical architecture making it all possible. Think about this for a second. When you ask a complex AI model like ChatGPT a question, what actually dictates its speed? You're probably picturing thousands of GPUs, graphics processing units, just crunching numbers in some massive, dark server room. And, well, you'd be partially right, but there's a huge, surprising bottleneck that most people completely overlook. The answer? It's the network. The absolutely crucial point here is that these massive clusters of GPUs don't just talk to each other through their standard CPUs. The true speed limit of AI training, the thing holding it all back, is the network connecting them. In the AI era, the network literally is the computer. So here's our agenda for today. First, we'll look at the AI network shift. Second, the great GPU bottleneck. Third, we'll break down spine leaf architecture. Fourth, microbursts and real-time monitoring. And finally, how AI is actually managing AI networks. Starting with Section 1, the AI network shift. Let's see how traditional data centers fundamentally differ from the AI era we're in now. Look at the contrast here. Traditional setups were built for things like e-commerce and web servers, so they had really predictable user-to-server traffic. We call this north-south traffic, just data flowing in and out to clients. But AI training, it completely flips the script. Now, you might have tens of thousands of GPUs working together, and over 90% of the traffic actually stays inside the data center, bouncing laterally between the GPUs themselves. We call this massive internal flow east-west traffic. Moving to Section 2, the great GPU bottleneck. So why exactly do these GPUs need so much insane networking power to begin with? Well, modern large language models are just incredibly massive. We're talking models with 70 billion, 400 billion, or even a trillion parameters. They are physically too big to fit onto a single GPU. So we have to slice them up and spread the workload out. The GPUs compute their individual layers, but then, and here's the catch, they have to constantly synchronize their math with each other in a process called distributed training. And this brings us to the absolute scariest part of the whole process. It's a synchronization phase called all-reduce. It sounds intense because, quite frankly, it is. During all-reduce, every single GPU in the cluster has to simultaneously exchange its gradient data to update the global model. It's just a massive, completely synchronized data dump happening all at once across the entire network. To put that into perspective, imagine a single GPU takes 100 milliseconds to do its math. But then, the network takes 300 milliseconds just to sync that data with the rest of the cluster. That means your incredibly expensive, state-of-the-art hardware spends the vast majority of its time just waiting. It's sitting completely idle. In an AI data center, the speed of your network directly dictates the speed of your model training. Let's jump into Section 3, spine leaf architecture. To solve this massive data traffic jam, network engineers had to completely rethink the physical layout of the data center. They created what's known as the spine leaf fabric. It's basically a giant, highly interconnected web. Data travels from a GPU server up to a leaf switch, then up to a spine switch, back down to another leaf, and finally to the destination GPU. What makes this so brilliant is that it guarantees consistent latency between any two hosts anywhere in the system. It supports multipath routing, known as ECMP, and it easily scales horizontally. So you can wire up an AI cluster with 512 GPU servers, 64 leaf switches, and 16 spine switches, creating a seamless fabric where no two GPUs are ever too far apart. Okay, Section 4, microbursts and real-time monitoring. Because even with a brilliant physical layout, the AI network faces a terrifying, almost invisible enemy. That enemy is the microburst. Since thousands of GPUs often finish computing their data chunks at the exact same millisecond, they trigger an instantaneous traffic explosion. We're talking about generating multiple terabytes per second instantly. This creates a massive digital traffic jam that causes switch queues to overflow and packets of data to be lost in just a fraction of a second. Now, for a normal website, dropping a few data packets is just a minor hiccup. The system simply resends them. But in synchronized AI training, it causes something called the straggler effect. A single dropped packet means one GPU gets delayed, and that means the thousands of other GPUs waiting to sync during that all-reduce phase, They all have to pause and wait for the slowest link to catch up. Your multi-million-dollar supercomputer literally grinds to a halt for a split second. Because these microbursts happen so insanely fast, sometimes just 10 or 100 milliseconds, traditional network monitoring is basically useless. The old standard check the network every 5 minutes. That is totally going to miss a 10-millisecond spike. Today, we have to rely on continuous streaming telemetry. Using protocols like OpenConfig or GNMI, switches constantly stream real-time data about queue occupancy and packet drops, giving us actual millisecond-level visibility. All this data feeds into deep network observability. When GPU utilization mysteriously drops from a super-efficient 95% down to a sluggish 60%, modern observability tools map the entire traffic journey, from host A up through the leaves and spines to host B. They analyze latency, jitter, and packet loss using advanced tech like in-band network telemetry, or INT. This lets engineers pinpoint exactly which link is lagging. And that brings us to our final section, Section 5, AI Managing AI Networks. This leads to a truly fascinating conclusion. Think about the scale for a second. When a data center network grows to hundreds of switches and tens of thousands of individual links, human engineers simply can't analyze it manually anymore. The sheer avalanche of telemetry logs and syslogs is way beyond our cognitive capacity to sort through in real time. So what's the solution to managing the network powering AI? Well, it's more AI. We call this AIOps. The AI system ingests massive amounts of historical data to establish normal baselines. For example, it learns that 20% queue usage is totally fine. But if there's a sudden spike to 80%, boom, it instantly issues an alert. Better yet, it automatically does the root cause analysis, figuring out instantly if the problem is a bad spine switch, a degraded optical module, a buffer overflow, or an ECMP hash issue. This brings us to the holy grail of modern infrastructure, the closed self-driving network loop. The AI observes the network like spotting a link at 95% utilization. It analyzes the root cause, decides on the best fix, like adjusting routing paths, and then actually takes action to fix it itself. This is a total game changer. In the future, network engineers won't be staring at logs, they'll be managing the AI agents that do the driving for them. This quote right here really captures the ultimate truth of the AI revolution. Everyone gets so hyped about the GPUs, but without a high-speed, exceptionally stable network, even the most expensive, cutting-edge GPUs in the world will be dragged down. The network is the foundation. In fact, the network is the computer. The hardware might get all the glory in the headlines, but the network holds the absolute key to performance. So who is going to master spine leaf fabrics, streaming telemetry, and AIOps to become the most critical engineer of the next AI era? Are you ready to manage the supercomputers of tomorrow? Thanks for tuning into this explainer. I hope this helped pull back the curtain on the real backbone of AI